This lecture is on section 2.6, derivatives and rates of change. So we've been doing a lot of work with estimating the tangent line by using an analytical approach of calculating y values and then subsequently calculating slopes and seeing what slope we approached, and therefore knowing the slope of a tangent line at a given point, and are able to come up with the equation of the tangent line based on that analytical approach. Now that we know limits, let's combine what we know about the analytical approach with our limits approach and make it faster for us to find the slope of the tangent line using a limit approach. So if a curve C has an equation f of x, and we want to find the tangent line to a point on that equation, then we consider the nearby point, and we look closer and closer to our desired point where the tangent line crosses through. And based on what the slopes are approaching, also known as a limit, we then can estimate the slope of the tangent line and then subsequently come up with the equation. So here's a diagram, which should be familiar to you by now. As we pick points closer and closer to P, the slopes of the line get closer and closer to the actual tangent line. Let's recall what we did. So recall that in order to estimate the slopes of a tangent line in an analytical approach, if we are using x squared as our function, you should go into your calculator, click y equals, and y1, type x squared. Remember to go to second window into the table set feature and ensure that next to independent, ask is highlighted, not auto. Then go second graph into the table feature and type in these x values, 1.9, 1.99, 1.999, 2, 2.001, 2.01, and 2.1, as we are approaching from the left and the right side. So if I fill in this chart based on what my calculator has told me the y values are, the y value for 1.9 is 3.61. The y value for 1.99 is 3.6901. Sorry, 3.9601. The y value for 1.999 is 3.996. The y value for exactly 2 is 4. The y value for 2.001 is 4.004. The y value for 2.01 is 4.0401. And the y value for 2.1 is 4.41. Now remember, although we've been working with limits for a while now, we're not actually interested in the y values. We're interested in the slopes, always compared to 2, 4, because that is where the tangent line is being drawn through. So we need to calculate a slope between all of these pairs. So we would calculate our slopes. Let me try to make a neater chart here. So we have x, y, slope. So our x is 1.9, our y value is 3.61, and our slope would be 3.61 minus 4 over 1.9 minus 2. Or I could have done it the other way around. It really doesn't matter. So 3.61 minus 4 divided by 1.9 minus 2 gives us 3.9 for the slope. Moving on to the next x value, which was 1.99, getting closer to 2, with the y value being 3.961. We calculate the slope of 3.961 minus 4 over 1.99 minus 2, and we put that into our calculators. 3.961 minus 4 divided by 1.99 minus 2, and that gives us the slope of, again, 3.9. So we have 3.9 here. Now let's do 1.999 with its y value of 3.996. I don't know why my decimal points are turning into these weird lines. There we go. So now let's calculate 3.996 minus 4 over 1.999 minus 2. Let's see, we get 3.996 minus 4 divided by, open parentheses, 1.999 minus 2 gives us a slope of 4. Now let's take a look at the other side of 2. So if we start another chart, and we are going to start at 2.1, the farthest away from 2 on the right side, with a y value of 4.41, we are going to calculate the slope. And again, always comparing to the desired point of 2, 4. Let me erase these out of the way. So we have 4.41 minus 4 over 2 minus 2.1. No, I got to put them in the same order. So the 2.1 goes with the 4.41, so that needed to go here. That's better. So now we have 4.41 minus 4 divided by, in parentheses, 2.1 minus 2, and that gives us a slope of 4.1. Now let's get closer to 2 by looking at 2.01. With a y value of 4.0401. So here we go. We have hold on, let me move some stuff out of the way. (4.0401) minus 4 all over 2.01 minus 2. Putting it in my calculator. Divided by, we get 4.04 as our slope. That's 4.04. Last one is 2.001 with a y value of 4.004. We plug that into our formula. 4.004. And we're going to divide by 2.001 minus 2. So 4.004 minus 4 divided by 0.001. And we get a slope of 4. So we can see as the slopes get closer and closer to the point in question, which is 2, 4, we are approaching 4. And the same is true when we approach from the right side. And analytically, we learned that that means we should estimate the slope of the tangent line to be 4. Using this definition to find the slope of a tangent line using limits allows us to go from that analytical approach, which is quite time-consuming, to something a little bit easier to streamline. So the definition states that the slope of the tangent line can be found by taking the limit as x approaches a. Notice no direction is indicated, meaning you have to take a look at the left limit and the right limit and make sure that they're the same, of the function minus the function at the specific value a over x minus a. So for example, if we find let's find the equation of the tangent line to the parabola x squared at the specific point 1, 1. So in order to do that, we'll use the limit formula by taking the limit as x approaches 1 of the function minus the function at 1 all over x minus 1. So our function f of x is actually x squared. So we're replacing x squared with its equivalent expression of f of x with its equivalent expression of x squared. So we have x squared minus 1 over x minus 1. We are taking the limit as x approaches 1, which if we do a direct substitution, we can see that we will get a division by 0, which is not defined. In this case, it's a simple factoring algebraic approach that we can use. If we factor the numerator, we can see that the group x minus 1 cancels, and therefore leaving us with just x plus 1. And a direct substitution works now to give us a limit of 2. So now, instead of doing that analytical approach from the left side and the right side, we found that the slope of the tangent line is 2 by using the limit definition. Using a point slope form of an equation of a line, we can use the point 1, 1 and the slope of 2 in order to get the equation of the tangent line y equals 2x minus 1. If h represents the step change between the x values, so going from 0 to 2 or whatever, then x is equal to a plus h. And so the slope of the secant line PQ can be found by the following. The slope of the secant line, remember secant line is an average velocity, not an instantaneous like the tangent line, can be found at the y value, h steps away from a, minus the y value at exactly a, all over the distance between the x's, which happens to be the step, which is h. Notice that as x approaches a and h approaches 0, so does the expression of the slope of the tangent line becomes a more complicated version. The limit as h approaches 0 of f of a plus h minus f of a all over h. This is the definition of a derivative, because a derivative is simply the slope of the tangent line. Let's use this definition to solve this particular problem. So we want to find the equation of the tangent line to this function at the point 3, 1, and we want to use the limit definition. So recall that the limit definition is the limit as h approaches 0 of f of a plus h minus f of a all over h, where in this case, our a is 3, and h stays h. So we are going to have the limit as h approaches 0 of f of a plus h, so that is f of 3 plus h minus f of 3 all over h. Now, f of anything, f of x, is 3 over x. So we are going to replace all the x's with this 3 plus h, and then we're going to replace all the x's with just the value of 3. So we have the limit as h approaches 0 of the function 3 over x, where x is 3 plus h, minus 3 over x, where x is 3, all over h. And this gives us the limit as h approaches 0 of 3 over 3 plus h minus 1 which if I wanted to be able to complete this problem, I will rewrite 1 as a very specific form of 1, 3 plus h over 3 plus h. And the reason why I chose to do that is because in order to subtract fractions, you need common denominators. And right now, I can't just take the limit because there's going to be a 0 in the denominator. So when we're working with the limit definition, our goal will always be to eliminate the h in the denominator. So now let's combine these terms in the numerator by distributing the negative sign. We get the limit as h approaches 0 of 3 minus h all over the common denominator of 3 plus h all over h. So 3 minus 3 cancels, and we have the limit as h approaches 0 of negative h over 3 plus h over h, and let's just put that h over 1. And the reason why I'm putting that h over 1 is so that I can see there's two fractions, a fraction divided by a fraction. If I recall from algebra, I'm going to flip the bottom fraction and multiply straight across. Now, when I do that, the h's now are allowed to cancel, and that problem with the 0 in the denominator has been removed. So I have the limit as h approaches 0 of negative 1 over 3 plus h. When we put 0 into the limit, we get a limit of negative 1/3. So now we know that the slope of the tangent line is negative 1/3, and we need to use the point 31 to complete the example of finding the equation. So let me clear this out, and then we'll complete the equation. Sorry. Okay, so we found that the slope of the tangent line is negative 1/3, and we're using the point 31. So using point slope form, y is equal to m times x minus x1 plus y1. We get y is equal to negative 1/3 times x minus 3 plus 1. Distribute to make this prettier. So we get negative 1/3 x plus 1 plus 1. Combine like terms, and y equals negative 1/3 x plus 2 is the slope of the tangent line to the rational function 3 over x at the point 3, 1. And we found this by using the limit definition of the slope of the tangent line. Let's take a look at this same definition, but in terms of velocities. So in general, suppose an object moves along a straight line according to an equation of motion, S equals f of t, where S is the original displacement directed distance and the directed distance of the object from the origin at time t. The function f that describes the motion is called the position function of the object. In the time interval from t, which is equal to a, to the next time t, which is equal to a plus h, the change in position of f of a plus h minus f of a is shown in this picture. Okay, so we can see that we have a and we have a plus some distance h. When we subtract that, we get the distance. The average velocity over this time interval is found by taking the displacement, the subtraction of this y value minus that y value, and divided by time, h, what time has passed. Now suppose we compute the average velocities over shorter and shorter time intervals. In other words, we let h approach 0. So we let h, the gap between the x's, get very, very small, which is what we did analytically as we were getting closer and closer to our desired variable. If we were focused on 2, we started at maybe 3, came back down to 2.5, 2.1, 2.01. Essentially, the gap between 2 and the value we are using to estimate the slope of the tangent line is approaching 0. which is where the limit comes in. So let's do this example. Let's suppose that we have a ball that is dropped from the upper observation deck of a tower, and it is 450 meters above the ground. What is the velocity of the ball after 5 seconds? Okay, well, let's come up with our equation first. So what we do know about position function when it comes to a free-falling object is that the position or the height of the object after time in seconds is equal to negative 4.9 t squared. And in this case, we're going to add the initial height. And the initial height of the ball is 450 meters. So our equation becomes negative 4.9 t squared plus 450. And we want to find the velocity of the ball after 5 seconds. So essentially, what is this asking? It's asking us to find the slope of the tangent line at x equals 5. Okay, let's do this using the limit definition. Now, because I don't have a whole lot of room on here, what I'm going to do is I am going to jump over to my whiteboard to do this problem. So again, we have the height of the ball after t seconds is equal to negative 4.9 t squared, and that number should be familiar if you've taken any physics class, plus 450. Now I am going to say we are going to take the limit as t approaches 0, h approaches 0, of f of a plus h minus f of a all over h. In this case, a equals 5, because we're talking about 5 seconds later. So we have the limit as h approaches 0 of f of 5 plus h minus f of 5 all over h. Now recall that f of is the same as h. I probably should have labeled these. Oh, I probably shouldn't have used h, huh? Let's change that. So instead of h of t, let's change this to a of t. A is not good either, huh? Because we're using a for something else. How about position? So let's use capital H, the height after time. So instead of f, we'll keep that because that's the definition. Let's put big H here. So we're saying using the height function, replace every t with 5 plus h, and then the second one says replace every t with the number 5. So we have the limit as h approaches 0 of negative 4.9 t, which is 5 plus h squared plus 450, minus, big brackets, negative 4.9 5 squared plus 450, all over h. So now we want to do our algebraic skills, and again, the goal will always be to eliminate the h in the denominator. So let's do some side work. We need to multiply out 5 plus h times 5 plus h, because this is a binomial squared. So we'll do the FOIL method, and we get 25 plus 5h plus 5h plus h squared, giving us 25 plus 10h plus h squared for the 5 plus h squared part of this equation. So we get the limit as h approaches 0 of negative 4.9 times 25 plus 10h plus h squared plus 450 minus a negative 4.95 squared, so that's plus 4.9 times 25, which is 5 squared, minus 450 as we distribute the negative sign. So now I need to distribute the negative 4.9 over here, and I can multiply this out. So I get the limit as h approaches 0 of negative 4.9 times 25, which comes out to be negative 122.5. Plus negative 4.9 times 10, which is negative 49h, and then multiply negative 4.9 times h squared, plus 450, plus 4.9 times 25, which gives us 122.5, and then minus 450. Oh, and all of this is still over h. So now I see I have a negative 122.5, which cancels with the positive 122.5. I have a positive 450 and a negative 450. This leaves me with all terms that have an h in it, which is exactly what we were looking for in order to eliminate the h in the denominator. So I have negative 49h minus 4.9h squared all over h. So the reason why I'm excited that there's only terms with h in it in the numerator is because now I can factor out an h in the numerator, which leaves me with negative 49 minus 4.9h all over h. And that allows me to cancel the denominator, alleviating that issue of dividing by 0 when I take the limit. I can now take the limit at 0, and that leaves me with a negative 49 meters per second is the velocity of the ball at 5 seconds later. Now, why is it negative? It's because it tells you the direction in which the ball is going. Since it's negative 49 meters per second, it is stating that the ball is going down, isn't towards the ground at 49 meters per second in speed. Now, the second part of that question asks us, instead of going back to the PowerPoint, let me just read it so that we can stay in the whiteboard. But it asks us how fast was the ball going as the ball hit the ground. So first we need to know how long did it take, big H. Here's our equation of marking the ball's height at any point in time after the ball had been released at 450 meters above the ground. In order to find out how long it took the ball to actually hit the ground, we have to set the height of the ball equal to 0, because the height of the ball when the ball's on the ground is 0, and we need to solve this quadratic equation for t in order to find how long it took the ball to hit the ground. So we subtract 450 on both sides. Since there's only one variable with t in it, we don't have to use a quadratic equation or anything like that. Divide by negative 4.9 on both sides. So negative 450 divided by negative 4.9 gives us approximately 91.84. Is equal to t squared. And then we take the square root of the last answer, square root of 91.84, to get the time it takes the ball to approximately hit the ground is 9.58 seconds. Now that we have the time at which it takes the ball to hit the ground, we can do the same thing we did in part 1 to calculate the velocity of that ball as it hit the ground. Now, after it hits the ground, obviously its velocity is 0, but it does have an initial velocity at the very instant that it touched the ground. It was going its fastest out of its entire process. So let's now calculate this. So 9.58. We need to find the limit as h approaches 0 of f of 9.58 plus h minus f of 9.58 all over h, where we're using the same equation. So we have Oh, let me write that over in the actual top of the screen. So we have the limit. Hold on. All right, limit as h, my whiteboard is crazy today. As h approaches 0, we have negative 4.9 t squared, which t is 9.58. Sorry, 9.58 plus a, just kidding, plus h squared plus 450 minus f of a, which is 4.98 negative times 9.58 squared. Ow, oh, drop my pencil. Plus 450 all over h. Now again, we have a binomial squared, so we got to do a little bit of side work. 9.58 plus h times 9.58 plus h. So we need to find 9.58 times 9.58, which gives us 91.7764 plus 9.58 h plus 9.58 h plus h squared. If we add our 9.58 h's together, we get 91.78 if I round, plus 19.16 h plus h squared, just for this binomial squared part. So I need to write that down before I don't have it in front of me anymore. 91.78 plus 19.16. Okay. Let's see what we have now. So we have the limit as h approaches 0 of negative 4.9 times the 91.78 plus 19.16 h plus h squared plus 450. Distributing the negative sign, we get a positive 4.9 times 9.58 squared. So that gives us times 91.78. And distributing the negative sign for the plus 450 would be minus 450. It's still all over h. We still have to take this front number and distribute it in. So we get negative 4.9 times 91.78, and that gives us a limit as h approaches 0 of negative 449.72 plus 4.9 times 19.16 gives me, oh, it's negative because there's a negative 4.9, so we have minus 93.88 h minus 4.9 h squared plus 450 plus 4.9 times 91.78 is 449.72 minus 450 all over h. Woo! No surprise at this step, everything but h terms with h in it should cancel. So our negative and positive 450, our negative and positive 449.72, leaving us with just values with h in it, so we can factor out the h. So we have the limit as h approaches 0. Let's factor out the h, leaving us with negative 93.88 minus 4.9h all over h. We cancel the h's out now, algebraically correct, and we substitute in our 0, and that leaves us with a velocity as the moment the ball hit the ground, to be negative 93.88 meters per second. Again, the negative tells us that the ball was going down towards the ground, and it was traveling at 93.88 meters per second the second that it hit the ground. Let's head back to the PowerPoint to finish up. So in general, derivatives, this is the definition of the derivative, taking the limit as the step between the x's gets closer and closer to 0, where you find the y value of the far x value, a plus h, minus the y value at the actual point that we're trying to draw the tangent line to, all over the change between the x's, reducing to as close to 0 as possible, hence the limit. So this is the formal definition for a derivative. Let's use this definition to solve this problem. Let us find the derivative of this function x squared minus 8x plus 9 at an undisclosed number value a. I'm actually going to use my whiteboard for this because I'm going to need more room. Oh, but I need to write down this equation first. X squared minus 8x plus 9. Okay. So we're looking at the function f of x is equal to x squared minus 8x plus 9, and we're looking at x equals just a generic value a. And it gets a lot harder when we're working with the definition of the derivative and we don't actually have a specific value for a. So we'll take the limit as h approaches 0 of f of a plus h minus f of a all over h. Remember, it is taking out all the x's in the f of x function, and in this first one is replacing it by a plus h for all x's. So we have the limit as h approaches 0 of x squared, which is a plus h squared, minus 8 times a plus h plus 9. So I rewrote x squared minus 8x plus 9, replacing the x's with the a plus h. Then we subtract, according to the formula, the entire function at a. So that would be a squared minus 8a plus 9. My 9 looked like an A there. And this is still all over h. Doing our side work, a plus h squared, we have to FOIL it out and distribute, giving us a squared plus ah plus ha plus h squared. Multiplication is commutative, so we have a squared plus 2 of these ah terms plus h squared. That is going to fit in here. We can take the negative 8 and distribute, giving us negative 8a minus 8h plus 9 at the end. That is now the whole first part of just this part. Then we distribute the negative sign through the next part of the equation, giving us minus a squared plus 8a minus 9. Still all over h, and we're taking the limit as h approaches 0. So now I'm going to go through, and my hope is that the only thing left is terms with h in it. So I have a positive 9 and a negative 9, a positive 8a and a negative 8a. I have a positive a squared and a negative a squared, leaving me with just terms with h in it. And my next step would be to factor out the h. So we're now at the limit as h approaches 0 of 2ah plus h squared over h. We factor out the h in the numerator to get h times 2a plus h over h. The h's cancel, we let the h go to 0, and the derivative is 2 times a, where a can be any number, and now we actually have a formula to find the slope of any tangent line to this parabola given a value a. And this concludes our section on 2.6.